This is your presenter Asloob Mudassar, and I am presenting slide number 142B of the course on laser physics. So this lecture must be read with the previous slide, which was slide number 142A. So this is in continuation of the previous slide, and here I am going to present ruby laser mainly and some part of the neodymium laser. Ruby laser. Natural form of ruby is a crystal of aluminium oxide Al2O3 called corundum. Crystal grown artificially from the molten Al2O3 is called sapphire. For ruby laser, the laser material is an artificial crystal grown from the molten mixture of aluminium oxide and a small percentage of chromium oxide, which is Cr2O3, by weight, which is included as 0.05% by weight. That is, some of the aluminium triply ionized ion, which is aluminium 3 plus ions, are replaced by chromium 3 plus ions in Al2O3 to act as a laser material. So you can notice that we are replacing some of the aluminium triply ionized ion in Al2O3 by some chromium 3 plus ions. And this is by weight of 0.05%. And then Al2O3 with the substitution of chromium ion will act as a laser material. A small amount of chromium makes the ruby to appear pink, and a greater percentage gives it a red color. The electronic configuration of chromium in terms of the electronic configuration of the argon is the electronic configuration of the argon along with the 3d5 and 4s1 will give you the electronic configuration of the chromium. So out of these one 4s electron and two 3d electrons contribute towards the ionic bonding, and there are 3 electrons left in the 3d shell which arrange themselves in 24 states which interact strongly with the crystal field of the host. There is an octahedral field at each aluminium site in the Al2O3 lattice. The energy levels shown in figure 142.1 are due to the interaction of a 3d electron of the chromium with the octahedral field. So let me show you that figure. This is the figure. The caption of the figure is relevant energy levels of a ruby laser. And you can see over here that these are the levels. We have 4F1 band, we have a 4F2 band, and the pumping is done from the ground state using 420 nanometer wavelength and 550 nanometer wavelengths. So these are the pumping wavelengths which are used to pump the ruby from its ground state, which is a 4A2 level, from its ground state to the upper states, which are 4F1 and 4F2. And from you see that these two states can also decay to the ground states. But before these two levels decay back to the ground states, there is a fast non-radiative decay from these 4F1 and 4F states to the 2E states. So these two states contains many levels, out of which I have shown only two prominent levels, which are 2A levels and E prime levels. So the 2A levels and the E prime levels are very strongly coupled levels. These two levels are very strongly coupled, and 2A level will decay spontaneously and very quickly, very fastly to the E prime level. So E prime level will act as an upper laser level, and 4A2 will act as a lower laser level for the lasing process. However, R1, which is from 2A to the ground state, can also be obtained. So here R1 will give you 692.8 nanometer and R2 will give you 694.3 nanometer. So R2 is a prominent wavelength and most intense wavelength can be obtained at R2. That is from the transition from E prime to the ground state for A2. So E prime will act as the upper laser level and for A2 will act as a ground laser level. So this is a rough idea that I have given you about this diagram. More will be given in the subsequent paragraphs. The energy levels shown in figure 142.1, which I have just shown you, are due to the interaction of a 3D electron of the chromium with the octahedral field. The level labeling is due to group theory. So you see that these notations that we are using are due to group theory, and I am not presenting that one. So you must take these notations as granted. All transitions are 3D transitions, because you know that since this is the electronic configuration out of which one electron from the 4s orbital and two electrons from these 3D orbitals will contribute towards the ionic bonding in the host material, and then we are left with the 3D, then we are left with the three electrons of the 3D. These electrons then will have 3D interactions. All transitions are 3D transitions. The multiplicity of 4F1, 4F2 and 4A2 is 4. You can see that these levels 4F1, 4F2 and ground state 4A2, these have multiplicity equal to 4. You can see that at the superscript we have 4 over here, so the multiplicity is 4. And the multiplicity is given by the formula 2s plus 1 is equal to 4, where capital S is actually the total spin quantum number due to the number of electrons present. So we have 2s plus 1 is equal to 4. And from here, if you solve this for the value of S, then you will get capital S is equal to 3 by 2. This capital S is actually the total spin quantum number due to the 3 electrons. So obviously it appears that the 3 electrons have a parallel spin. So each electron have a spin equal to half. So 1 half plus 1 half plus 1 half will give you 3 half. So it means that all the 3 electrons in the 3D transitions will have total spin equal to 3. So this total spin quantum number arises from the 3D electrons which have parallel spins as far as these states are concerned. Pumping is mainly done from the ground level, which is 4A2 level, to the bands 4F1 and 4F2 using wavelengths 420 nanometer and 550 nanometers respectively. So here you can see that the pumping is done from the ground state level, which is 4A2 level, to the upper bands, which is 4F1 band and 4F2 bands. So the pumping is done from the ground state to these two states using these two typical wavelengths, which is 420 nanometer and 515 nanometers. For F1 and for F2 decay to 2E levels very rapidly in a non-radiative way. So you see that these bands for F1 band and for F2 band can also decay to the ground states, but before they decay to the ground states, they will decay very quickly to the 2E states non-radiatively. So this is a non-radiative decay from 4F1 to 4F2 to the 2E state, to the 2E band, you can see. So for F1 and for F2 decay to 2E levels very rapidly in a non-radiative way. 2A and E prime are strongly connected and there is a very fast non-radiative decay from 2A to E prime. So you see that I have in connection with the 2E levels, I have shown only 2 levels over here. So these 2 levels are very strongly coupled and 2A will decay very rapidly to the E prime state, to the E prime level. So 2A and E prime are strongly connected and there is a very fast non-radiative decay from 2A to E prime. The level E prime is thus heavily populated. The transition from the 2e to the ground state, which is 4a2, is spin forbidden. The decay time is very long, of the order of 3 milliseconds. The level E prime is separated from the level 2A by 29 centimeter inverse, which is much smaller than KT divided by HC is equal to, which is equal to 209 centimeter inverse. So this corresponds to thermal energy in centimeter inverse. That's why to obtain the thermal energy in centimeter inverse, I have divided KT by HC. So KT divided by HC will give you 209.209 centimeter inverse, which is the which is much small, which is much smaller at 300 Kelvin. So E prime, being more populated, is considered as the upper laser level and 4A2 as the lower laser level. So in this band of 2E levels, the E prime levels is considered to be heavily populated, and so this will act as the upper laser level for, and 4A2 will act as the ground laser level. So the transition from E prime to 4A2 will give you R2 wavelengths, which is 694.3 nanometers, and this is a very intense transition. However, the other transition, which is R1 from 2A to 4A2, is also possible, which I shall be explaining soon. A less probable transition from 2A to 4A2 can also contribute a second wavelength to a ruby laser. Ruby is analogous to a three-level laser system and thus requires strong pumping, because there is no level below the ground laser level. That's why it resembles the three-level laser system. That's why a very strong pumping is required, as in case of three-level laser system. Therefore, a very strong pumping is also required for the Ruby system, for the Ruby lasers to operate. At 300 Kelvin, lambda is equal to 694.3 nanometer is homogeneously broadened, with broadening in terms of frequency. Delta nu naught is equal approximately equal to 11 centimeter inverse, or in terms of frequency 330 gigahertz. The main cause of this broadening is the interaction of the chromium triply ionized ion with the phonons of the lattice. Typical diameter of a ruby rod lies in the range from 5 to 10 nanometers. From 5 to 10 millimeters, with the rod length lying in the range from 5 to 20 centimeters. Pumping is done with the flash lamps in pulsed form. Laser is thus obtained in pulses. As the laser has a large line width, short mode-locked pulses of the order of 5 to 10 picosecond interval can be produced. So you see that mode locking is also very easily obtainable in Ruby lasers. Q switching can also be easily implemented due to long lifetime of the upper laser levels. And you know that I have mentioned that the lifetime of the upper laser level is very high, of the order of 3 milliseconds. So Q switching can also be easily implemented due to long lifetime of the upper laser levels. The gain at lambda equal to 692.8 nanometer is smaller, and any dispersive element in the laser cavity can be used to select lambda is equal to 694.3 nanometers. So you see that here from these transitions, you can see that R1 has a wavelength of 692.8 nanometer, which is very smaller, which is very weak transition in comparison with the transition, which is R2, which has a wavelength of 694.3 nanometers. So we can reject R1, and if we want to obtain R2, we can produce any dispersive element in the cavity, and we can get rid of R1, and we can make R2 to laser in the laser system. So R2 can be obtained very easily using any dispersive element. For CW operation, a very intense transverse flash lamp pumping or an organ ion laser beam longitudinal pumping can be used. So if you want to use a transverse pumping, you have to use the flash lamps. But if you want to concentrate on the longitudinal pumping, then organ ion laser can be used. Requirement of intense pumping is a weak point of ruby lasers. Pulsed nature of ruby lasers with operating wavelength in the active region of the photographic high resolution materials make the ruby lasers ideal for pulsed holography. Ruby was the first laser operated in 1960. Now a brief introduction of the Neodymium. Neodymium laser, usually abbreviated as ND laser. In ND lasers, some of the triply ionized ions in a host material are replaced by triply ionized neodymium ions, that is ND3 plus ions. So if you have a host material, you can replace some of the ions in the host materials by the ND3 plus ions. If the host material is YAG, which is the yttrium aluminium garnet, having the formula Y3Al5O12, some Y3 plus ions are replaced by the neodymium 3 plus ions, and the doped material is called ND-YAG. Possible host materials are some fluorides, for example, YLI, yttrium lithium fluoride, YLIF4, vanadate, YVO4, phosphates, and silica and silicate glasses, etc. These are the possible host materials for the Nd:YAG laser. The magnitude of doping depends on the relative sizes of the dopant ion and the host ion. If the dopant ion, which is ND3 plus ions, if the dopant ion's size is much larger, a small concentration of dopant ion is recommended, as large concentration could strain the host crystals. ND3 plus ions is nearly 14% larger in size than the Y3 plus ions. The transparent undoped material, when doped with ND3 plus ions, give a pale purple look due to the absorption of the ND3 plus ion in the host material, or in the host material in red. But this is a very small introduction of the neodymium ion. In the next slide, we shall give you detailed description of the Nd:YAG laser and ND glass lasers. So this is the end of slide number 142. That is part B of slide number 142.